Hi everyone, welcome back to week 12 of MEM 230068 Apply Fluid and Thermodynamics Principles in Engineering. We are continuing from last week, week 11, and now we're going to discuss further on the application of the gas processes. Usual before this course start, this online recording is intended for internal teaching within South Metropolitan TAFE Carlisle WA campus only. You may not either directly or through the use of any device or other means copy, download, upload, publish the content unless expressly permitted by South Metropolitan TAFE in writing. Okay, so on the week 11, last week we pick up how import we discuss multiple gas processes, including constant pressure, constant volume, isothermal, adiabatic, and polytropic. Today we're going to see how we're going to use that gas processes in heat engine. I just brought up this formula sheet as usual. It should be on your Dropbox file. This formula, as you see, this is going to be used on your exam, so please make sure you are familiar with the content. And some of the formula, such as the surface area of the circle or the volume of cylinder, are not here, so please make a note of that. Just quickly recap from last week, we discussed constant pressure. So in this formula sheet, the constant pressure is named isobaric. So iso is stand for standard or constant. So baric is for pressure. So isobaric constant pressure. You can see here the work delta U change of internal energy and Q heat transfer is ready on for your disposal. Isochoric, choric is a chamber, hence is constant volume. Isothermal, as we discussed last week, and polytropic and adiabatic. Technically, polytropic and adiabatic formula is very similar, except you have to change N to gamma. So N polytropic index, gamma is adiabatic index. And in adiabatic process, there is no transfer of heat. So Q in this case is 0. While in polytropic, there is a transfer of heat. Some processes can be, for the polytropic and adiabatic, can be expressed like such. So we use this expression quite handy. Properties of the air, Cp, Cv, R is all given here, so you don't have to scramble during the exam to find where all the numbers are. Now, why we are discussing the multiple processes of gases? Well, we kind of want to discuss how the heat engine is working. For our purpose, we're going to just limit ourselves to um, four-stroke engine and diesel engine. Although there are other many processes like two-stroke and Stirling, we're not covering it in this course, but principally is using the same uh, gas processes that we're going to discuss. So what is a heat engine? Heat engine is a device that continually converts heat to work or power. So the words continuously is very critical, because if it doesn't produce the power or the work continuously, it's not a heat engine. Now, this heat engine, for your information, if we look at the component, we have a heat source, then we have a heat being supplied through a medium, whether it's gas or water or whatever, goes into the heat engine. There is a work being produced. There's a heat being rejected to heat sink. So we have essential um, items in the heat engine. You should have a heat source, working substance, mechanical work or power output, working cycle, and heat sink. Now, heat sink is generally colder than heat source. When we say colder, doesn't mean it can be touched. Colder is in essence that if you supply the heat at 1500 degrees Celsius, the heat sink can be 1000 degrees Celsius, so you can't touch it, but it's colder in the sense that it's colder than heat source because the heat is being consumed by the heat engine to convert the energy into the work or power. Now, if you notice on this diagram here, we go the other way around. Instead of work being produced, we put work into the system, and instead of rejecting the heat from the sink, we actually taken the heat from the sink and rejected to the source. What do we have? We have a refrigeration cycle or air conditioning system. So the heat sink maybe is our room. We try to maintain at 24 degree. Outside summer 37 degrees Celsius. Naturally, the heat wouldn't flow from 27 to 37, but with the help of the work coming in into the heat engine, or in refrigeration cycle we call it reverse heat engine, we actually manage to reject or transfer the heat from the less temperature, which is 24 degrees Celsius, when we put it out into ambient, which is 37 degrees Celsius. So we're not going to cover the refrigeration cycle here. You will have another units covering the refrigeration cycles later on. Now back to this heat engine diagram. Under steady state condition, this formula is fixed, so you don't have to modify it. If you look on your formula sheet, formula for heat engine, work equal to Q supply minus Q reject, which is the same here. And if it's become power, which is rate of energy, then you put dot on it because it's gonna be rate of the heat being supplied and the rate of the heat being reject. So there is a time involved. Efficiency, work over Q supply, power over Q dot S, which is the same here. Okay, so this is a heat engine. I have put this scan into Dropbox, and you can have a look and browse around. So efficiency of heat engine is like that, and it's called thermal efficiency. The reason it's called thermal efficiency because this is the efficiency which the heat energy is converted into mechanical energy. So it doesn't calculate the theoretical maximum efficiency. It's a good enough to calculate overall efficiency, although it's not that accurate in the real world. In the real world, you can't just take how much the heat being produced divided by the heat being supplied. That doesn't work in real world because you have a bearing loss, you have friction loss, you have other loss and things like that. But for overall efficiency, this is your formula: output divided by input. Now, we also have what we call the limiting efficiency. So the limiting efficiency is basically the maximum efficiency theoretically that you can achieve with such of the machine. So Carnot formulate this efficiency, and then they call it Carnot efficiency or maximum possible efficiency. And the formula is very simple. It's just based on the temperature C for cold, which is the sink temperature, and TH is T hot, is the temperature of the source. So back to this diagram again. Temperature of the sink divided by temperature of the source, and 1 minus those answer. But do remember, this temperature must be in kelvins, like that. So in exam, if you are asked to find what is the Carnot efficiency or what is the maximum possible efficiency, you have to convert the temperature from Celsius to Kelvin, which is you will. Anyway, as discussed last week, we have to convert all the temperature to Kelvin and the pressure to absolute. Quickly, we have example here. Question A, if an internal combustion engine using atmospheric temperature as a heat sink at 20 degree and temperature after combustion is 1450 degrees Celsius, what is the maximum possible efficiency? You convert 20 degrees Celsius, which is the cold temperature, plus 273 become 293 Kelvin, and the hot temperature 1450 plus 273 is equal 1723 Kelvin. So 1 negative that, and 0.83 is the maximum possible efficiency of that particular engine. Of course, we will never reach this in our real life, but many people use this as a benchmark to maximize their efficiency. If you look, maybe the best practical application on this is probably on Formula One. So Formula One engine is very small engine with super aerodynamic body and a lot of tweaks to maximize the efficiency of that particular engine as close as to the maximum possible efficiency of the heat engine, which is never be achieved. But there's a technology there which people try and spend a lot of money, and of course for entertainment, racing the cars and see which one betters. We will also considering the Carnot cycle. So in Carnot cycle, if we look in this graph here, this is similar to what we discussed last week. So in Carnot cycle, from 1 to 2, there is a compression. So V1 get compressed into V2, and the compression is isothermal, as you can see here. From point to 3, the gas is further compressed, but it compressed adiabatically, means there is no heat transfer or heat gain between 2 and 3. After that, after reaching point 3, the gas is expanded again at isothermal, and further expanded again quickly by adiabatic. So that is the Carnot cycle. Now, this is a theoretical engine cycle, which is not going to be achieved in the real world. But this is but we can use this as a model. So the formula of the Carnot cycle, just go back here. Oops, sorry. So the Carnot cycle will be governed by this formula as well as this formula, the efficiency, and the maximum possible efficiency. Okay. Next, we want to discuss about Otto cycle. Otto cycle is a four-stroke positive displacement internal combustion spark ignition open cycle. If you know the Posty bike, the old Posty bike, not the new one. The new one is electric, but the old Posty bike, there's a four-stroke engine. Our cars normally run on four-stroke engine, the fuel one, not the diesel one. We will going to discuss the diesel cycle a little bit later. Now, if you don't know how the engine looks like, this is a very simple explanation. If you Google in internet, there's a lot of more interactive animated cycle, which is I encourage you to have a look and get yourself familiar with the cycle. Basically, cycle 0 to 1, we draw the air from this intake valve. You can see here there is a spark plug, so spark plug will ignite the mixture of the air and gas mixture of the petrol and the air. In your car, normally the spark plug would be replaced every now and then. I do remember back then in Indonesia, I have a small 100cc motorcycle. I replace the spark plug quite often because in Indonesia, as you know, it's always flooding. The one is flood and the water get the engine and it damages the spark plug. Anyway, back to this. So from 0 to 1, the air is being drawn into the cylinder, so the piston moves downwards, creating a vacuum, so it's drawing air down. You can see these three lines here is a piston ring. When the piston ring is new, they normally seal quite well. As the engine travel quite a lot, the ring scratches the internal wall of the cylinder and then got worn out, so we have to replace the piston ring. If you don't replace the piston ring, you can see a white smoke coming out from the exhaust, and over the time the cylinder also not become smooth anymore, become a scratch, and we lost the vacuum, so we have to clean the cylinder and we have to make it smooth again. So that's involving a lot of work by bring the engine down. So when the piston goes down, create vacuum is draw the air mixture into the chamber. And this piston goes down to about here and it can't go down further anymore because of the linkage. So what we call is bottom, we call this position as a bottom dead center position. From there, the piston goes up again, the intake valve is closed and the air is being compressed, hence it's called compression stroke. Piston goes up to the top, and again at the top they can't go further, and then we call this position top dead center. So once it's at the top, the spark plug ignite, and there is an explosion in this little chamber. So this explosion will push the piston down very, very quickly. So from 3 to 4, we call it expansion or power stroke. After that, it reaches at the bottom dead center again, and at this time, the outlet valve is open, letting the air goes out. After that, the piston goes up again and push the remaining air out. So from 4 to 0, this is where the air goes into your exhaust pipe at the back. Theoretically, if you plot it into the PV diagram that we discussed last week, so atmospheric pressure, the air is being drawn. So this air here, maybe at point 0, is mixed with a little bit of petrol into 1. And then from 1, 1 to 2 is compression stroke, so it's been compressed. And it compressed very quickly. So at that particular time, there will be no heat transfer. Of course, if you compress it 1,000 times, then will be a heat transfer. Hence, we have a heat sink or radiator to cool this cylinder. But we only look at one particular time frame here. So it's being compressed at adiabatic process. After that, from 2 to 3, it further compress. But if you look from 2 to 3, the piston is already at the top, so it can't go further up anymore. Hence, the chamber, the little chamber of gas here is fixed. So from 2 to 3 is constant volume combustion, as we discussed last week. From 3 to 4, after the combustion, the piston got pushed down very quickly to the bottom, and hence is adiabatic. So 1 to 2 compress very quickly, adiabatic. 3 to 4 expand very quickly as adiabatic. From 4 to 1, the gas is again um, losing the pressure at a constant volume. So if you look 4 to 1 here, the piston is already at the bottom dead center. It can't go any lower, so this chamber of gas here is also fixed. Hence 4 to 1 and 2 to 3, where the piston at the top dead center is a constant volume process. From 1 to 0 is get pushed again out as constant pressure, because the valve is open in 1 to 0 and 0 to 1. The valve is open means the pressure in this chamber is equal to the atmospheric pressure, and the volume, sorry, the pressure is always constant, but the volume changes. So it's getting smaller or getting bigger or getting smaller. That's the theoretical diagram. The actual diagram is more like that, is a bit undistinguished. Which one is constant volume, which one is constant pressure, whether it's adiabatic. It looks like adiabatic all the way, and then that not really constant volume is look either isothermal or polytropic. So that's what happened in real life. For our purpose in this course, we're just gonna use theoretical PV diagram. Now, advantage and disadvantage of Otto cycle. Well, the advantage, they are capable running at high speed and high power output per unit mass. If you see most of the sport car or a supercar, they are running on auto cycle, they're not running on diesel cycle. Well, nowadays you got Tesla, which is electric motor. That's different discussion. Anyway, not they're not using internal um, heat engine cycle, so we're not going to discuss that. That's another interesting topic. Now, the the disadvantage is, as you know, all the engine are noisy and prone of vibration and pollution. So we have a catalyst converter at the back of our exhaust. This actually even worse in diesel cycle. Now, the main disadvantage of this auto cycle four-stroke engine is they are low power outputs. Hence, they're not suitable for pulling very heavy load. All the cruiser ship or semi or the trucks or heavy duty vehicles, they normally use on diesel cycle because they have a high power output. They are required to produce a very high torque in order to pull or push a very heavy load. The theoretical work and efficiency for the auto cycle, you, you will see this formula is the same as your formula here. So you have to apply a particular formula according to the cycle. So whether it's constant pressure or constant volume or is adiabatic. So you just need to follow this. Now let's consider an example. So example 6.4, if you have your book with you, otherwise just follow up in this online whiteboard. I'm just going to pull my whiteboard. There. So have a look. Example 6.4 here. I drew the PV diagram for auto cycle. So auto cycle is from 0 to 1, constant pressure. 1 to 2 will be adiabatic compression. 2 to 3, constant volume combustion. 3 to 4, adiabatic expansion. 4 to 1, constant volume expansion. Oops, missed the arrow here. Now let's read the question very carefully. It is said the compression ratio is 8 to 1. Now this means V1 here would be 8 times more than V2. So V2, that's a V1, which is true, means volume at 2 is 8 times smaller than V1 because it's being compressed that way. So we arrange this expression, we just say V1 over V2 equal to 8. So this is our expression. We're going to save it for later. Next, let's have a look. Inlet condition is 97.5 kPa absolute, so it's already in absolute. We don't have to convert it again. T1 is 50 degrees Celsius, so we do have to convert that into Kelvin, which is 323 Kelvin. And the heat being supplied is 950 kilojoule per kilogram. Where do you think the heat being supplied? The heat is being supplied here. Remember, from 2 to 3 is internal combustion. So 2 to 3 is compressed, and then the spark plug will ignite, then is combustion. So the heat is being added here. We're just going to do Q supply. And where's the heat being exhausted? Well, the heat is being exhausted here, because this is an exhaust cycle. Q exhaust. So I think we have enough data to start this question. Let's have a look. Question A. So question A, what is the maximum cycle temperature? The maximum cycle temperature will occur not at point 2, but at point 3 after the heat being supplied. So we need to find T3. So I'm just going to write here, the maximum cycle temperature is T3. T max. In order to find T3, we need to find T2 first. So let's have a look from cycle 1 to cycle 2. So cycle 1 to cycle 2. And we know cycle 1 to cycle 2 is adiabatic. If you look on your formula sheet, so the gamma, the adiabatic index for air, is 1.4. Let's have a look our formula sheet to adiabatic process. So adiabatic, we can use this formula, we can use this formula as well, but for adiabatic, replace N and N with gamma. So our aim is to find T2 first in order to find T3. We know T1 is 50 degrees Celsius. Let's find T2. So what I'm going to use this one, T2 over T1. So T2 over T1 equal to, I'm not going to use the P2 over P1. Instead, I will use the V1 divided by V2 to the power, not n, but gamma minus 1. So T2, that's what we're after. T1 is 323 Kelvin equal to V1 over V2. Have a look here. This is what we already established before, the compression ratio. So V1 over V2 will be 8 to the power 1.4 minus 1. So solving for T2 equal to 742 Kelvin. Now, how to find T3? Well, let's have a look. 2 to 3. So 2 to 3 is a constant volume. process or isochoric. Let's have a look the isochoric process here. So you can use this formula. Isochoric process, P over T equal to constant. Why is that? Remember from last week we say P2 V2 over T2 equal to P3 V3 over T3. But we have a constant volume. So this V is the same. Now the problem using this formula is, yes, we do know T2, we do not know P2, or we do not know P3 either. We might need to use different formula. So let's have a look the formula for isochoric. Let's see what is given here. So maybe we can use the heat transfer formula because the heat is being given, isn't it? The heat coming into the system is 950 kilojoule per kilogram. Mass of air we can assume is a kilogram. We know the CVR air. T3 instead of T2 we know, oh, that's what we after, and then minus T2 instead of T1. So we can use this. So let's use that expression. We can't use that, scrap it. Let's use Q being supplied equal to mCV, in this case T3 minus T2. Now T2 we already calculate that is 742 Kelvin. We can say is 1 kilogram. Q supply is 950 kilojoule per kilogram, so we just assume 1 kilogram. CVR of air you can see from the formula sheet, 0.718 kilojoule per kilogram Kelvin. Careful in here, this is kilojoule, there's a kilojoule. So this unit is the same. If this is joules, you have to convert this into joules. Multiply by T3, this is what we after, minus 742 Kelvin, which is T2. Solving this, our T3 is 2065 Kelvin. If you put it in Celsius perspective, is 1792 degrees Celsius. It's pretty hot. This is our maximum cycle temperature. So the cycle temperature wouldn't go beyond this. Let's have a look the next question. Question B. The indicated work per kilogram of air use. So question B is asking about work. Oops. Now, work in here occur when the piston goes up and when the piston goes down. Okay. So work happen during the constant pressure. It does also happen during the adiabatic process. Now to calculate every single work on each process, it would be cumbersome. What we're going to do for work, we're going to use this formula. Work equal to Q supply minus Q reject, which is gonna make life much easier rather than calculating work for each process. So we're going to say, oops, work equal to Q supply minus Q reject. Now we know Q supply is from 2 to 3. Q reject is from 4 to 1. So 2 to 3 constant volume. 4 to 1 is also constant volume. We know Q supply 2 to 3 is 950 kilojoule per kilogram. We don't have to calculate that. We only need to calculate Q reject from 4 to 1. So let's have a look. 4 to 1. So 4 to 1 is constant volume or isochoric. Now if you look on your formula sheet, the constant volume formula for Q reject is QR mCV T4 minus T1. The mass of the air here would be 1, CV is known. We know T1 is 50 degrees Celsius, but we do not know what T4 is. So we need to calculate T4 first before we can find this. Let me clean the board first. Okay, let's find T4 first. So to find T4, we need to look process 3 to 4, which is adiabatic. I will use this expression again. So will be T4 over T3 equal to V3 V4 comma minus 1. Now we know T3, we calculate that. We're looking T4, V3 of V4. Well, let's have a look this expression again. So V1 and V4 is the same because it's constant volume. So I can rewrite this. So V1 is actually V4 is the same. V2 is the same as V3 because it's a constant volume. Now we have V3 over V4, so we simply going to reverse that. So V3 over V4 equal to 1 over 8. Okay, so we have all the information. T4 divided by T3 that we calculated before, 2065 Kelvin equal to 1 over 8, 1.4 minus 1. Just going to put a line here so you're not getting confused. Solving for T4 is 899 Kelvin. Now come back to this equation. So Q reject equal to M, 1 kilogram. CV of air, 0.718, again kilojoule per kilogram Kelvin, multiplied by T4, 899. T1 is 50 degrees Celsius, so it's 323 Kelvin. Q reject equal to 413.5 kilojoule per kilogram. So now we can calculate the work being done. So the work being done equal to Q supply 950 kilojoule per kilogram, negative Q reject 401.3.5 kilojoule per kilogram. So the unit is kilojoule, is the same. So work being done 536.5 kilojoule per kilogram. Okay. Now the last question, question C. What is the efficiency? Let's clean the board again. Question C. What is the efficiency? Now the efficiency here is referring to thermal efficiency. Remember our early discussion, we have two types of efficiency. One is thermal efficiency, the other one is maximum overall efficiency. Question C doesn't state anything, so we're going to assume this is our thermal efficiency, not the maximum theoretical efficiency. Efficiency of heat engine will be this. Efficiency equal to work output divided by Q supply. Our work, we already calculated that, 536.5. Q being supplied is this 950, is given by the problem, and efficiency is 56.5%. Now, in the exam, you might be asked, well, okay, so that's thermal efficiency. What about the theoretical maximum efficiency? If that question being asked, then what you'll do, you look on the formula sheet. The maximum theoretical efficiency is 1 negative T cold over T hot. In this case, the cold temperature is 50 degrees Celsius, so 323 Kelvin, and the hottest temperature is, we calculate question A before, it's 2065 Kelvin. So the maximum theoretical efficiency is 84.4%. This is 56.5% is the thermal efficiency or overall efficiency, while 84.4% is theoretical maximum efficiency or limiting efficiency. It wouldn't go far beyond this. The last cycle I would like to discuss today is diesel cycle. So this cycle is the same, is positive displacement, four-stroke internal combustion, and invented by Rudolf Diesel as far as 1860s. There is a bit of similarity between diesel cycle and Otto cycle. The only difference is after the adiabatic compression, the combustion takes place at constant pressure rather than constant volume. So we see before in Otto cycle, the combustion goes up like that. In diesel cycle, the combustion goes at constant pressure instead of constant volume. And again, this graph is also theoretical, it's not the actual Otto cycle. The difference of the Otto cycle is the compression ratio is 12.1, sometimes as high as 18 or 20 to 1, while Otto cycle is 10 to 1. I know in some of the sport car like Subaru, they are using high compression ratio. The higher the compression ratio, the more efficient the fuel is going to be used because the air can explode very easily at higher compression. So you don't have to spray too much fuel, hence saving your fuel. However, the drawback means the engine has to be stronger. If you use a stronger engine, generally the material is heavier and is adding the weight into your car. Although some car try to use very alloy material, but that's become expensive. Diesel engine doesn't have spark plug because the air is gonna combust anyway at very high compression ratio. Oh, another thing, if you use high compression ratio car like a Subaru or a certain manufacturer like Holden's or Toyota 86, I think I'm pretty sure, you can't use unleaded 91. They recommend to use 95 or 98 high octane to achieve a perfect combustion. Diesel engine doesn't have spark plug but have an injector at the cylinder, will inject fuel directly into cylinder, and that gonna causing an explosion in the system. Diesel engine load control is achieved by varying amount of fuel injected and not by throttling the air inlet. So the air inlet in the diesel engine is almost constant. The advantage is the most efficient because of course it's only use a little bit of fuel in order to produce the power that you want, and at very high compression ratio the fuel is burned the gas mixture burned very easily and most likely achieve close to the perfect combustion compared to the Otto cycle. Another advantage that people like to use diesel engine is they are very reliable. Like Toyota Land Cruiser run 300,000 kilometers or more, or a big truck or a cruise ship. They just very, very, very reliable. Even submarine using diesel engine. Although the new one they use nuclear power because with diesel engine the enemy will pick up the vibration from the submarine and they're going to send a torpedo into that particular submarine. But it's been used in submarine quite a long time ago before the nuclear power is used or invented. The disadvantages is they have lower specific power output, hence they don't have a quick acceleration, but they will produce very, very high torque. So Lamborghini is not diesel engine because they are speeding from 0 to 60 mph in a couple of seconds. And diesel engine is actually very causing too much pollution. There's a lot of research into that, although the fuel is less volatile and less vaporization to atmosphere, but the diesel fuel itself is very volatile, and a lot of people with asthma, apparently they can pick up the trace of diesel fuel even though after being filtered, and they trigger the asthma again. Let's have a look the application of diesel engines. So this is the cycle of diesel engine. I do have an example here, which is I don't have it in the book. So we have a diesel engine. It's drawing air at 20 degrees Celsius. So T1 here at 20 degrees Celsius. I already converted into Kelvin, 293 Kelvin. Drawing pressure at 100 kPa absolute. The compression ratio is 21:1, which means V1 here, V1 is 20 times more than V2, because as we go here, the air is being compressed to smaller volume. So we arrange this V1 over V2 equal to 21. The question also state that or give information that volume after combustion is twice of that before combustion. So remember, in diesel engine the combustion occur from point to 3. So volume at 3 after the combustion is twice than before combustion. So V3 is 2 times of V2. We arrange that V3 over V2. Do we have another information? I think that's it. So I'm just going to draw here. This is the heat being supplied. That's combustion. 4 to 1 is the same like Otto cycle, so that's the heat being reject. Let's have a look at the first question. The first question, question A, find the temperature at each state. So T1, T2, T3, T4. So T1 we know is given. Let's find T2. So in order to find T2, we have to look the cycle 1 to cycle 2. So cycle 1 to cycle 2, remember the diesel engine is adiabatic, and this adiabatic compression, adiabatic expansion from 3 to 4. So 1 to 2 is adiabatic. If you look on sorry about that. If you look on your formula sheet on adiabatic, there is an expression like that. T2 over T1 equal to P2 over P1 to the power gamma minus 1 minus gamma equal to V1 over V2 gamma minus 1. So in this case, I'm not going to use P2 over P1 because I don't know what's the pressure at point 2 is, but we know V1 over V2 is 21. We know the adiabatic index for air is 1.4. So T2, that's what we're after. T1 is 20 degrees Celsius, 293 Kelvin is equal to 21 to the power 1.4 minus 1. So T2 here is 990 Kelvin or 717 degrees Celsius. to save that. So T1 done, T2 done. Let's have a look T3. So from to 3 is constant pressure. We can use this equation if you remember from the last week. P2 V2 over T2 equal to P3 V3 over T3. Now this is constant pressure, means pressure at 2 will be the same at pressure at 3. So we're going to delete. These two will cancel each other. So we're not going to use it. We're going to rearrange. We want to find T3. So T3 equal to T2 multiplied by V3 over V2. So I just move T3 into here and move T2 on the other side. I move V2 to the other side. We know T2, we already calculated that, 990 Kelvin. V3 over V2, have a look here. So V3 over V2 is 2 because the question said the volume after combustion is twice of that before combustion. So T3 equal to 99 Kelvin, 990 Kelvin multiplied by 2, which is that. That's give us 1981 Kelvin or 1708 degrees Celsius. Okay, so T3 done. The final one is T4. So from 3 to 4 is adiabatic again. Adiabatic expansion. 1 to 2 was compression. So we're going to use the same formula again for from 3 to 4. T4 over T3 will be equal to V3 over V4 to the power gamma minus 1. Now we don't have V3 over V4 expression here, so we're going to um, deduce it from what we have so far. Let's have a look here on this chart. V1 and V4 is the same because they are constant volume. So we're going to write here V1 is equal to V4. So we can rewrite this. Instead of V3 over V4, we're going to say this is V3 over V1, right? Because V1 equal to V4, so I'll just gonna replace V4 with V1. Now we can further break this. So I'm just going to write V3 here multiplied by V1 here. It's technically still the same, V3 over V1. But we're going to say, how about, I'm just going to change the color. How about we divide this by V1, sorry, V2, and then we'll put V2 here. So V2 cancel. The final result is still V3 over V1. That correct? Now V3 over V2 is 2. Here, have a look here. V3 over V2 is 2. V2 over V1 is the inverse of this, 1 by 21. So V3 over V1 is 2 over 21. Alright, now back into this T4 again. So T4 divided by T3, 1981 Kelvin equal to 2 over 21 to the power 1.4 minus 1. So T4 is 773 Kelvin or 500 degrees C. So T4 is found. Next question is question B. So question B is asking the work done per kilogram of fuel. It's the same like the Otto cycle before. What is the work being done? Let's clear the board. So work in this case being done here from 1 to 2. So 1 to 2, there is a work input. 3 to 4, there is a work output. And 4 to 1, there is a work output too. Now like before, we don't want to calculate the work at individual stage. So we're going to use the heat engine work instead. Remember, work equal to Q supply minus Q reject. And we're going to assume the mass here is 1 kilogram because it's not given. Question 223, sorry, not question 223. Process 223 is constant pressure. So QS 1 from 2 to 3 is constant pressure. If you look on your formula, equal to mCp T3 minus T2. So 1 kilogram multiplied by 1005 kilojoule per kilogram. We know T3 1708 minus 717. Q reject is from 4 to 1 is constant volume. So MCV now, not CP, T4 minus T1. So again is 1 kilogram, 0.718. T4 was 500 minus 20. So if you notice here, I'm actually using the degree Celsius temperature instead of the Kelvin. If I wrote it down, was T1 was 20 degrees Celsius or 293 Kelvin. T2 was 717 degrees Celsius or 99 Kelvin. T3 was 1708 degrees Celsius or 1981 Kelvin, and T4 is 500 degrees Celsius or 773 Kelvin. Because this is delta T, or the temperature different, it doesn't matter whether you use Kelvin or Celsius because the difference will be the same. So apologies for the confusion. If in your exam, I probably suggest to stick with Kelvin. So whatever T3 in Kelvin, so instead of write 1708 degrees Celsius, write 1981 Kelvin instead. Anyway, so back to this. So work QS 995.995 minus 344.64. So we have 651 and 355. The unit is kilojoule. Remember, kilojoule, kilojoule, kilogram, kilogram, cancel, kilogram, kilogram here cancel, and Kelvin and Kelvin, Kelvin, Kelvin cancel. So the unit is kilojoule. The next question, question C, what is the heat being supplied per kilogram of fuel? So he's asking what is the heat that coming in from point 2 to 3. So question C, heat being supplied per kilogram of fuel. So as you can see here, the heat is being supplied from 2 to 3. So if you look, process 2 to 3 is constant pressure. Q equal to mCp T3 minus T2. So again, 1 kilogram multiplied by 1.05 kilojoule per kilogram Kelvin. Now T3 1708 minus 717 Kelvin. So the heat being supplied is 996 kilojoule. The last question is, what is the thermal efficiency? Remember, the thermal efficiency is not maximum or limiting efficiency. So thermal efficiency simply work output divided by the, the heat being supplied. In this case, our work was 651 kilojoule and the work being supplied is 996 kilojoule. So the thermal efficiency of the system is 65.4%. Just the last of the last, what is the Carnot efficiency? So the Carnot efficiency is the difference between T cold over T hot. Now this T cold you have to use Kelvin, so the coldest temperature is 293 Kelvin or 20 degrees Celsius, and the hottest was 1981 Kelvin. So the Carnot efficiency in this case is 85.2%. So that's all for today. Please practice these questions at your own pace, and I will see you next week.